Good afternoon, my name's Nick. I'm from EPCC in sunny Edinburgh, and I'm talking about program productivity and performance on embedded RISC-V CPUs. And really, this is some research we've been doing, and we've just started a project to pull this more into production and really aiming to connect with the RISC-V community and the tools community here. So if I was to say Internet of Things, edge computing, well, everybody's heard of this because it's such a popular area that's hyped up at the moment. But obviously this area of embedded computing really is important and really is critical and massively growing area. And one where, no surprise, RISC-V is popular, continues to see significant growth and opportunities now and to the future. But, one of the big challenges here is it can be a real pain to program these things. Even the experts, it can be very time consuming because typically these things are running bare metal, lots of cores in a chip, maybe tiny scratch pad memories, and they've got connection potentially to larger, slower memory areas, but there's a big penalty if you don't leverage them correctly. And this can often put these in the domain of the few experts. So a few years ago, we started on a project looking at a tiny implementation of Python called Epyson. And the whole idea was to enable somebody to go from 0 to hero in less than a minute. So with no prior experience or very little of programming these embedded architectures, being able to get something running. And memory size is absolutely crucial here. We've limited ourselves 24 kilobytes with this initial version. And for instance, this is way smaller than things like MicroPython. Now, this was initially developed for Adaptiva's Epiphany. Unfortunately, that went out of business quite some time ago. So we ported it over to RISC-V because of the great ecosystem, because of all the CPUs that are part of this. And commonly in RISC-V, we're running on a 16-core soft-core Pico-RV. So it looks like that on a Zinc. And this is a configuration for some of the results I'll show you in a few slides' time. And this worked fine. It worked really, really well. But the interpreted nature of this means that the performance is pretty poor. Great for education, great for getting people onto this. But actually to use this for a serious company, even for fast prototyping, the performance was severely limiting them. However, maybe what you can see from the layout here is it was all very modular. So yes, we had this interpreter, but we've also been able to add in this native code generator with the idea of, hey, let's use this to improve the performance. So we've been developing a compilation approach. The high level is translating Python code down to C, which is then compiled using RISC-V's GCC. But this isn't a simple transliteration. Instead, what we're doing is we're compiling it down on top of an abstract machine representation, which then gets folded in at compile time. And it does this via macros. And for instance, we have macros for floating point computation. So if you're targeting a core where this has to be done in software, or maybe it can be done on hardware, or maybe you have to heavily vectorize it, well, it's just a slightly different macro. Macros that control all the memory layout, because we don't have the memory for things like libc. And we've got an example here of that, where we have a function, it's adding 2 integers up. So for instance, it does this lookup int macro, and then in the environment, which is this thing here, goes to scope level 0, and then the first argument, and then the same for the second argument. Obviously, this is all completely hidden from the programmer. They just see Python, but this is what this translates into. And functions also live in this idea of an environment. So here we're declaring a function that is this add thing that then points to this here. And whilst, yes, this does add extra layers of indirection, it gives us a huge amount of flexibility over and above doing this just directly in C without these macros. And one example of this is actually in these functions, because here, this is the example I just showed before with these macro expansions, but actually we can use this load procedure one instead. And what that's effectively doing is it's fetching this procedure from somewhere else, maybe the host, maybe network, maybe the file system. And all the functions are split up and segmented in this form. And we don't need to do this at program load. Instead, we can just put this empty placeholder in the environment and do it when we need it. So effectively, you can say, right, I'm going to call a function. Is it there? Happy days, just run it. If not, well, I'll go and fetch it. I'll pull it in, I'll execute it. And a bit later on, if I'm running out of memory space on these IoT cores, then I'll just flush out or garbage collect the less frequently used functions. So we can effectively run unlimited code sizes in these tiny memory spaces. So another similar benefit is on data itself, because yes, this environment approach points to the data, but the data doesn't physically need to be there. You know, for instance, often with these, we have a memory hierarchy where we might have the on-core memory, we might then have memory on other chips in the die, maybe then we've got some external DRAM, maybe then the file system and the network. So for instance, being able to say, look, I'm going to grab the data if it's there, work with it straight away. If not, then behind the scenes, completely abstracted from the programmer, go down, fetch it, pull it in from wherever it is, and then allow them to process it. And we've got things like a simple prefetcher to enable optimization of this. So one of our benchmarks, we've got something like 4 or 5 kilobytes of space, and then utterly transparently, we've got hundreds of megabytes of data just going through this, completely hidden from the programmer. As they say, the proof of the pudding is in the eating. So fairly simple benchmark. So we've got Jacobi solving Laplace's equation for diffusion. At the top right, what we've got here is size. So this is all in bytes. This C entry is native code we've developed to try and be as tight as possible. It took us quite a long time to get this size. The top one is the interpreter. So that's the size of the interpreter in the runtime, and then our bytecode. And this thing here is the version that I've just explained, where we're doing this dynamic loading. And this value is the size of our bootloader, but also the biggest function, because that's effectively what's controlling the amount of memory, the minimum memory size you need. And these are just some other configurations to experiment with this. So this dynamic dispatching approach, but where we don't do the loading, we put it all resident on the CPU beforehand. And then at the bottom, we've got just a quick performance comparison. So this is the RISC-V Pico-RV, the 16-core soft core. It's also very portable across architectures. So we've got this, as I say, this old Epiphany. We've got microblaze and then some other architectures as well. And in blue, we've got natively written C. Again, took us quite a lot of time, low level, really optimized it for the architecture. And then in stripy orange, just the Python code, which is just being portable across these different architectures. And as you can see, it's pretty close in terms of the performance. I mean, for comparison, our original interpreter, which I've not shown, is about 400 times slower than the native C implementation. So way slower. So, you know, for a small performance impact, you get all the program productivity of Python. And as I say, just being able to write these things really quickly and run them. So just to conclude this lightning talk, as I mentioned at the start, we're starting on a project to pull through this research into a usable state by developers, really targeting at the RISC-V CPUs. Our general architecture isn't just tied to Python. That's not the only game in town. It's actually a standard interface. Maybe I shouldn't say this, but we've also got a basic front end. I know it's not a very trendy language, but really that was just to illustrate that this is portable between different languages. And we can also target different architectures as well. For instance, different types of RISC-V CPU and tune them for these different ones. And certainly the Pico-RV is very simplistic. And we are now looking at other slightly more advanced RISC-V CPUs, really to look at exploiting these and leveraging these and trying to really tune our approach for them. So thank you very much for listening, and it'd be great to chat via the Q&A today. And here's my email address at the bottom as well.